Okay, let me start with the second slide, and then I'll go back a slide here. So far this unit, we really haven't covered a whole lot. We either worked with either pendulums or springs. Okay. With the idea being that these things operate not in a linear or a quadratic type of motion, but in what's called periodic motion. Typically, they either go back and forth or side to side. Okay. One of the biggest issues then with talking about things that undergo periodic motion is we can't use any of the kinematics equations. Usually. Here's the biggest reason why. Most of the kinematics equations involve something traveling with a constant acceleration, but the acceleration is often changing. Okay. Imagine a pendulum going back and forth. Okay. As the pendulum's over here, the acceleration is trying to pull it back this way. But then as the pendulum swings back over here, it still has acceleration, but it's trying to pull it back this way. And so the acceleration is not constant. The acceleration is changing from one side to the other. Does that make sense? Another issue we often have with trying to use kinematics equations in some of these formulas, sometimes, is that the velocity is often changing as well. Because the velocity is like over here at 0, then it picks up, then back to here at 0 again. So some of the formulas that we'd like to use, they don't work quite as well. Okay. My goal today is now to stop working with things swinging side to side, but I mean, imagine a kid on a swing, swinging back and forth, now all the way around the circle. So the idea being, rather than it just having like an arc length along the bottom, we've got to do the entire thing. Okay. Here, one thing does change about velocity though. As you were going back and forth, the velocity would go 0, speed up, slow down, 0, speed up, slow down, 0. Does that make sense? As it goes around the circle, though, the velocity should remain constant. Does that make sense? So it does bring back in one of our formulas, the d equals v over t formula, because that formula involves a constant velocity. So we can actually use that formula sometimes when working in circular motion. Here's the only issue. As you go around in a circle, the distance you travel is not actually a straight line, it's around the outside of the circle. And so for some of you in my math class, we talked about how to solve that. The circumference of a circle is 2 pi r, with r being in radians. So I'm going to show you guys how to solve the overlap, because some of you guys are in my Math 30 class and know how this, maybe know what I'm talking about here. And for those of you guys who aren't, I'll show you some examples of that later. Does that make sense where we're going the next couple of days then? Okay. Before I do that though, let me go back to this first slide here then. Since we're not working with linear or quadratic motion and we're working with periodic motion, this is the most common like shape of a graph we'd have, where you have the back and forth, back and forth, back and forth. And one of the most common words I need to reinforce is the term period. Could someone define the word period for me maybe?
How long it takes for it to go in.
Sure, that's probably better. I mean, length of time is good, but maybe a little more specific. It's the length of time it takes something to, how about we use the word repeat itself? Okay. Whether that means back and forth, or from now on in a circle, all the way around the circle is once. Again, around the circle twice. So, I mean, it still has like a repetitive pattern to it. Okay. This is what I was trying to hint at here. Instead of starting and stopping though, circular motion objects will actually have a constant velocity. So we can actually sometimes find velocities then. A few more pictures before we start in terms of like calculations. I found this diagram online. This could be like a pendulum, no, not a pendulum, a spring, like bouncing up and down. And hopefully you kind of get where I'm saying the same thing over and over again. Here's that same oscillating wave pattern going up and down and up and down. If you were to have a rotating wheel, something going around in a circle, it actually does the exact same thing. Imagine this is the height of the wheel above the ground. As you were to rotate the wheel, it goes up to the top and then back down, below, up, down, up, down, up, down. It actually has the same shape to it. Does that make sense? Kids in my Math 30-1 class, hopefully it really fits because I put these units together for a reason. This is essentially what we're doing in Math 30-1 right now. Okay, let's talk some theory behind circles then. Okay. I'm going to do what I'd hate doing. I'm just going to read off my slides. It's probably the best way of doing it right now. Okay. Although objects in circular motion have a constant speed, they don't have a constant velocity. Pause for a second there. What's the difference between speed and velocity? Velocity has a direction. Okay. When you're going around in a circle, it might always be going 5 meters per second, whatever that speed is. But the direction that the thing is traveling is always changing. It has to be, because it's going in a circle. Right? For a while, it's going this way, then this way, then this way, then this way, then this way, until eventually it comes back to where it was. Okay. So the direction of travel is always changing. There's a term I need to review with you guys. I think I showed you this in our first unit. Instantaneous velocity. Do you guys remember that word? That would be the velocity at any one moment in time. For example, let's say I use this picture right here. Here is a something going around in a circle. At any one moment in time, this red pendulum bob is actually traveling that way right there. That makes sense. And then at the blue section, it's actually traveling this way. And if I were to keep going here, if it was right here, it would actually be attempting to travel this way. Does that make sense? Let's say the string were to break. If I were swinging something around in a circle, if the string were to break right at this moment right here, this thing would take off at a tangent. Do you guys remember what a tangent is?
Like this from the circle to parallel.
That kind of works. Can you say your definition too, Jack?
So the line that only touches the circle once.
Yeah, it's a line that just barely touches a circle. This is a tangent where it just barely touches a curve. Okay. So that's instantaneous velocity, but rather than calling it instantaneous velocity, we're going to use the term circular velocity. Because we've got to be very specific. A velocity in a circle is very different than a velocity in a straight line. But if the string were to break, would this thing now travel in a straight line? I'd say, yeah, now it would. Okay, here's probably the more important thing then. Because the velocity is always changing, a change in velocity must mean there must be an acceleration. Does that make sense? Change in velocity implies acceleration. So there's actually acceleration on anything that's going around in a circle. And you guys probably know this intuitively. If you were to, say, drive in a vehicle and someone were to take a corner very quickly, your body, your inertial mass, you might like end up leaning in the car a little bit as someone like takes the corner too sharp. You ever experienced this before? That's actually an acceleration that your body is feeling. Okay. Last thought on this slide here. If there was no acceleration, the object would travel in a straight line. Newton's first law is the inertia law. Objects in motion will stay in motion unless a force acts on them. Why does this red ball not just keep traveling this way? Well, there must be some sort of force acting on it. Tension, yeah. The tension in this rope right here. Well, tension is a force. A force must be equal to mass times acceleration. Therefore, there must be an acceleration happening. Does that make sense? Okay, the term I need you guys to know then, we call this centripetal acceleration. And you guys back? Just noticing that it's logging in and out. Hope you guys are back. We call this centripetal acceleration. I looked this up over the weekend. Apparently centripetal is Greek for center seeking. Okay. The idea being that because of this thing, oh, we lost you. Are you able to see me on the video chat? Okay, let me just reset it. Just bear with me, guys. Because the speed is the same, that's one thing, but the velocity is changing because the direction is always changing. So if velocity is changing, there must be acceleration. Does that make sense so far? Which way does the acceleration go? Well, I hope this diagram helps make sense. Say you had a ball or something going around in a circle here, and the velocity was going this direction here. Eventually, the velocity will now be going this direction here. Does that make sense? Therefore, which way is the acceleration? Well, the acceleration is pulling you in towards the middle. The acceleration is the tension in the string pulling it inwards. If it didn't get pulled inwards, this thing would just fly off at a direction instead.
So does that mean force times speed equals acceleration?
Mass times acceleration, but sure. Yeah. That makes sense so far? So long story short, I guess I need you to know the velocity would try to take this thing off at tangents in all directions. But in order to prevent the ball from going off at a tangent, an acceleration, which essentially is based on your tension times, like your mass times acceleration being your tension, is going to cause this thing to actually get pulled into the middle, and that middle thing is going to keep the ball going in a circle. That makes sense? Okay. I've got a lot of pictures, but so long as you get the concept, I want to take you to some calculations. One more thought here. If you can have acceleration going into the middle of a circle, then that should also be a force. Now, I've been using the word tension so far. Tension's actually not a bad word to use, but not everything is held by a rope that goes in a circle. Okay. So rather than use tension, we actually have a term for that. We call it the centripetal force. Okay. So sometimes that centripetal force is tension, but it's not, it doesn't always have to be tension. That makes sense? Okay, hopefully I've made my point. Let me show you some formulas and we'll do some math examples. Okay. So there are two formulas I need you guys to know. They're both on your data sheet, and they're the ones that we skipped. I don't know that anyone thought of this beforehand, but when we learned about kinematics in that section there, I never showed you these two formulas because, well, we weren't ready for them yet. The difference here is that these guys have a small c down here, meaning these are only applicable if things are going in a circle. I think the C actually stands for centripetal. That's like the official Greek word for it. So these formulas, I could prove where they came from, I think, but I'm not going to. It's probably not worth our time, but I would like to point something out, especially for those of you guys in my math class, the 30-1 class. 2 pi r, 2 pi radians is all the way around the circle in terms of 360. And 4 pi squared just means that that's being squared, because that would be 2 squared is 4 and pi squared is pi squared. So hopefully you guys in my math class kind of can see where some of these things come in. This has to do with being in a circle. Okay. One last thought, then we'll do some actual examples with math here. Centripetal force, by the way, is not really a force on its own. We actually just mean that it's the net force when something's going in a circle. So when I talk about centripetal force, it is the net force when you go around in a circle. So let me do some examples, because that's probably the best way to start. So imagine that you are swinging something around in a circle. Okay. So there's a rope. You could say there's tension in the rope. But would this logic make sense here? The only force that we have is the tension force. So that force would be equal to your net force. And that force then would be equal to your centripetal force. Really, they're all going to be the same thing. The only force we have is tension in a rope that you're swinging around in a circle. That force is the net force, and that force is the centripetal force. So, normally, how do we find a net force? Sure. Here's our problem, though. The acceleration that we want to use has to be a circular acceleration. So I need the formula for a circular acceleration, which, going back a slide, is either equal to v squared over r, or could also be equal to 4 pi squared r over t squared. So I could either use this half of the formula for my acceleration, or I could use this half of my formula, depending on what information I have. So let me walk through this here. We have a mass. So there's a mass. We also have a velocity. And this guy right here, what's this information going to be? That's your frequency. Good job. Yeah. If you go around the circle 5 times in 1.25 seconds, how long does it take to go around once? Well, 12.5 seconds divided by 5. What'd you get? 2.5? 2.5 seconds. Actually, technically that's your period. But if you were to then do like 5 divided by 12 seconds, that would be your frequency. If seconds is on the top, it's period. And if seconds is on the bottom, it's frequency. So we actually have period. Any thoughts as to how I could somehow solve this? What am I looking for? No, we're looking for the length of a rope.
Oh, well.
What variable is that then? R. We're looking for R. Look at your formulas here.
Oh,
the centripetal acceleration is equal to v squared over r, but it's also equal to 4 pi squared r over t squared. It's not really a system of equations other than it's this equation equaling this equation is a good place to start. So what you could say is that the centripetal acceleration could be equal to v squared over r. We don't know what r is though. But isn't that centripetal acceleration, according to that formula, also equal to 4 pi squared r over t squared? And we know v squared. And we know t squared. We actually didn't need to know what mass was, apparently. Apparently mass wasn't actually important in this one here. So let me plug some, well actually before I plug numbers in, it may be better to do some algebra first. How in the world am I going to get r by itself based on this?
Like bring them out to the side, and then R would be,
Okay, so you'd have v squared equals 4 pi squared. If you bring r up to the side here, it'd become r squared.
and then bring the t squared up to.
Okay. So now what are you suggesting, Heather?
If you bring the t squared up to the other side and then just divide it by the 4 pi squared,
Okay, that'll work.
then r squared by yourself.
So v squared over 4 pi squared times t squared would equal r squared. And then to get r by itself, I'd square root everything. So that would really be vt over 2 pi equals r. I know my velocity. Don't I? 2.65 meters per second. I know my period because we just found it by dividing those numbers. So that was 2.5 seconds. And we're dividing by 2 pi. The seconds will cancel, which is good news because what's the only unit I have left? Meters. Isn't that a good unit for a radius of a circle? So I just need some help with calculations. 2.65 times 2.5, and then divide by 2 pi. Jack.
There's an easier way of doing this if you just use the velocity formula.
I was gonna mention that last there. I probably made this a lot tougher than I had to because I could have just used, there was another formula. I probably could have just used this formula here. I didn't think about that until afterwards. I'm glad that it works either way though. It's just a lot more work. This formula right here would really be velocity, what? Times time, divide by 2 pi. Yeah. I did a lot of work that I didn't have to do today. Thank you. Okay, when you divide by 2 pi, don't forget to put it in brackets. That's a huge common mistake. What'd you guys get?
Square?
1.05?
I got, yeah, it's
What,
2
1
pi
point-
squared?
No, it's just 2 pi, not squared.
Oh, why is it?
1.05? It shouldn't change everything so long as you do this guy squared, divided by 4 pi squared all in brackets.
Oh, I got it wrong. Wait.
Should I do this myself in the calculator? May as well. So take 2.65 times by 2.5 and then divide by 2 pi. 1.05 I got? Okay, 1.05. With sig digs, how many sig digs do I get though?
Unless no one uses the mass, and we get 3.
We didn't use this mass.
Yeah, but we, from our period, we only have to.
Well, okay, so we only wrote down 2.5, but we probably should have wrote down 2.50 because this had 3 sig digs. This 5 times right here was probably exactly 5 times, not like 5.0000. So I wouldn't count 5 times as 1 sig dig because that's probably exactly right on the dot 5 times. Well, no, because if this was just one sig dig, that probably wouldn't work. That wouldn't make sense. Like, this is the number exactly 5. Like, kind of like how, like, the number 2 right here, that wouldn't count for your sig digs either. So 1.05 meters makes sense. Does that work? Okay, let me try another one. Let's try to find the centripetal acceleration of someone going around a traffic circle. You guys drive around traffic circles ever? Okay, here's one of our first issues though. 40 kilometers an hour is not in proper units. We gotta put it into meters per second. So you're gonna have to, what is it, multiply by 1,000, divide by 3.6? Or no, yeah, multiply by 1,000, divide by 3,600. 11.111. Repeating? Okay. Okay, so for a formula here to find centripetal acceleration, this one's really easy. It's just v squared over r. So take your 11.1 meters per second, repeating there, square it, and divide by your radius. Oh, good call. Thank you. I wasn't paying nearly enough attention. This would be 60 meters for the radius, because that guy would be your diameter. Thank you. Good catch, guys. It's Monday for me, apparently. I already made 2 like mistakes. In terms of sig digs, when you divide the 120 by 2, I would say it'd be 60.0, but this 40 kilometers an hour only had 2 sig digs. So, you guys get an answer? 2.1 meters per second squared. One more thought here. We should throw a direction on this. This would be the direction. The acceleration of things going around in the circle is always inwards. So the acceleration that you'd be feeling would be this way, or this way, or this way, or this way. You're always going to feel centripetal acceleration. Feel like you're getting pulled to the middle. Any questions so far? To be honest, it's actually really straightforward. It's just using these new formulas. Okay. Have you guys ever seen one of these devices before? It's what NASA uses to train their astronauts to be used to high levels of G-force. You guys remember talking about G-force earlier in the year? It basically is a measure of like how many 9.81s you have in terms of like how much acceleration there is. So to help them get ready for a lot of gravitational like acceleration when you're on a rocket, they spin them around in a circle. Now, the circle part just means that they can keep going around without having to travel a lot of distance, but you still get acceleration. Okay. So here's the information I gave. We got a 100 kilogram man, a 8.8 meter centrifuge, and I gave 15 RPMs. We want to find centripetal force. Centripetal force then is really the same thing as your net force. This is kind of where I was going on a previous question. I kind of screwed up. To find a net force, it's mass times acceleration. But the acceleration we need has to be a centripetal acceleration. So, which formula for acceleration is probably more useful? The one involving velocity or the one involving period? Okay, so which is that one? That one was 4 pi squared r over t squared.
But that's a frequency, isn't it?
Okay, but I can convert a frequency to a period. Yeah, let me do that in a second though. Actually, let's do that right now. Let's go over here. That 15 RPMs, ugh, that's an M, really means that you go 15 times in 1 minute. We don't usually work in minutes though. So how do I convert that to seconds? 15 times in 1 minute, multiplied by 1 minute. oh my goodness, I'm having a horrible day writing things, over 60 seconds, and that would cancel away your minutes. So really divide by 60. Okay, so 0.25 times in 1 second. That's a frequency. Sure, so then this is going to be a reciprocal, which is awesome because that's 20-1, that's your topic for the day. So when we talk in math today, we're going to talk about a reciprocal. A reciprocal basically means 1 divided by that. So if you were to like do like a -1 symbol and flip it upside down, your period, I believe, is 4. Is it 4 seconds? So like one way of doing that would be to go 0.25 and then go 1 divided by 0.25. Another way of doing it, there's a button on your calculator. If you go 0.25 to the -1, that's the same sort of thing. Okay, I think we're ready to solve this thing. We have all the numbers we need. Let me just make some room. Come on in, if you can hear that. Come in. Thank you.
You guys are deaf.
You guys can come on in whenever it's breakfast time. Don't worry about waiting. Anyone get an answer? 6.91? Thank you, guys. Okay, so mass was 100 times 4
I think we're on the right track.
pi squared times the radius was 8.80. And then we're going to divide by the period, which was 4 squared. 2171? What's wrong, Nicole?
I got exactly what you got, but I got 21 instead of.
Oh, did you multiply by 100 for the mass?
No.
Okay, that's why.
Oh, I got that too.
Excellent. Okay, so I got 2171. What units would this be in? Good, newtons. The reason why it's in newtons is this is a force. This is either your centripetal force, but to be honest, that is your net force. It's the total of all the forces acting on you. So in terms of sig digs then, yeah, that 15 RPMs limits us to 2. So let's go 2.2 times 10 to the 3 newtons.
Should I do my direction on that?
In terms of that force, that also would be inwards. Because just like the acceleration pulls you inwards, so does this centrifuge pulling you in the whole time. Straightforward? I hope so. To be honest, for the most part, a lot of the questions we do, most of the questions, are very much just, well, now we're just using new formulas. I mean, you just gotta be able to figure out which formulas to use and when. What do I got for examples? You guys want to take a break now? You ever had that before where you're like, if my steering wheel does not actually turn slightly, I would just go like straight over the edge and die a horrible death. Fortunately though, my car works properly. And fortunately for one more thing, there's friction. Because the friction between the tires in my car and the road will actually cause my car to start turning. Because if there wasn't friction, then you guys watched that Magic School Bus episode, you'd just keep going straight over the edge. So we're looking for radius. Which formula do we have that works with radius? We have a couple. Probably one of the best ones to use would be acceleration is equal to, what was it, v squared over r? No. That one works? It's one of my formulas? I don't remember here. I have to memorize these ones too now. Where are those formulas again? There you go, v squared over r. And that's probably a good one to use because I have velocity. Because this guy right here is my velocity. Could we convert that real quick, go to meters per second? Could someone find that for me? 30.5 repeating?
Yeah.
Okay. Okay, so we have a velocity. Here's the problem. We got to find our acceleration if we're going to try to make this work. Okay. Here's the trick to this one right here. What force is acting on the car? Friction. That's actually the only force. Wow, okay. In the up and like in the side to side direction, friction is going to hopefully allow your car to kind of keep going inwards. Because if you don't have friction keeping your car from skidding, yeah, you'd go flying off the edge of the cliff. Does that make sense? But that's really like the only force acting. And so I said this earlier, the net force is really known as the centripetal force, but the only force we have is friction. So you could say, long story short, the force of friction is your centripetal force. It's the thing keeping you pulled towards the middle of the circle. If you don't have friction, you don't get pulled towards the middle of the circle. Lisa, could you grab the door again, please? Who was the last person in? Delver and Taylor. Okay. What's the formula for force of friction? Okay, but force normal, in this example here, we have no reason to think otherwise. Shouldn't it just be the mass times gravity?
Yeah.
Because isn't...
Mass.
Ah, watch this. How would we find that centripetal force? Well, it would be mass times the acceleration. Oops. Sorry, this is the really ugly looking, I didn't do a good job of it, a U for like the U.
It looks like a perfect upside down.
FM. Yeah, it does, doesn't it? Okay. Okay, hopefully some of you guys caught that epiphany. We don't know what the mass is. We don't need to. Mass right here and mass right here actually effectively cancels. So we don't actually need to know what mass was. Okay, we need to rearrange this formula set though to get radius by itself. For the most part so far this year, I've been okay if you put numbers in first, but it's probably better if we actually put the numbers in last because this radius is on the bottom of the equation.
Just kind of like focus on the round.
Yeah, radius has to go up top here, and then the u times g has to come down. So the formula we require is radius, come on, work a little board, will be equal to v squared over coefficient of friction times gravity. That should get us radius by itself now.
Then don't you prefer root?
No, because this radius is just r by itself. So then our velocity was that 30.5 repeating meters per second squared. Coefficient of friction was 0.60. And gravity, I don't know why we wouldn't be on Earth. It would be meters per second squared. Okay, one thing about units here, this guy has meters squared and seconds squared. This guy right here has just a single meters and a second squared. So if this guy has double meters, but this guy only has 1 meters, one of the meters cancels. If this guy has double seconds and this guy has double seconds, the seconds would cancel. So our unit should be in meters. Anyone get an answer?
1.6 times 10
What was the number before you did scientific notation? Okay, thanks. Pushing it a little bit, guys. So 1.6 times 10 to the 2. Okay, so the point I wanted to make on this one here, it's probably not harder, but the issue is just getting set up. And so I want to just point this out again. Often in solving problems, the centripetal force is the net force, and that net force is often something like either tension or friction. Tomorrow we're going to talk about what happens when it's gravity. But usually what happens is this FC formula has to equal like another formula, and then we use that to help solve. The cool thing about this one though, mass was irrelevant. We didn't actually have to know the mass of the car. Cool. All right, let's try another one. There's a 50-gram mass on the end of a 20-centimeter string, and you spin it in a vertical circle. Let me just draw a quick picture here. So, here's the center of the circle. This is 20 centimeters, and you're going to spin this around in a circle like this. I tell you that we measure the circle. We did 10 exact circles in 15.7 seconds. What does this information here help us find? Sure, period of frequency, basically. Depending on which way I divide them. If I want to find my period, then, do I do 10 divided by 15.7 or 15.7 divided by 10? Yeah, if we do the 15.7 seconds divided by 10, then it's 1.57 seconds is my period. Frequency would be doing 10 divided by it would be the reciprocal. So I have period. I have, this guy right here is a radius. Although what do I have to do to this radius to make it work in our formulas? Okay, so this will have to be 0.20 meters. Now we want to try to find the tension in the string at two different points. When the mass is at its highest point, when it's at its lowest point. Right now, the mass is probably at its highest point. What forces are acting on this thing at this particular point right now? Gravity's one. Tension's another. Yeah. What was that? Well, there's not really a normal force because this isn't like sitting on ground or anything like that. But I would suggest that at this point right here, you have gravity trying to pull it back downwards. What was that?
Why would it be different at the highest and lowest?
Let me see that I can explain this. Which way would the tension on the string be pulling back? No, back. It's pulling it in. Because if the tension doesn't pull this thing in, the thing would snap and go off other direction. So the tension is pulling it in as well. Those are your two forces. Those are going to have to be equal to your centripetal force then. So our formula is this. Our tension, plus our gravity is going to have to be equal to our centripetal force. Here's where this gets different. What if it's at the bottom? Let me just draw a different picture here. At the bottom, the tension is going back in, but gravity is going down. So then on the bottom one, you could say that the force of tension minus the force of gravity would be equal to the centripetal force. You guys see the difference there? At the top, gravity is actually trying to pull this thing back down, but the tension is also pulling it back down. So they're both working together. So what will actually end up happening is when you rearrange this formula here, the tension will be equal to your centripetal force minus gravity. Because gravity is pulling it back down, there should be slightly less tension. But at the bottom right here, gravity is pulling it down, and that's adding to your problems. So then on this example here, when you want to find tension by itself, it'll be your centripetal force plus the force of gravity. Gravity at the bottom is going to make it worse, but gravity at the top is going to make it slightly better. Does that make sense? I actually have a diagram on the next page that I found on the internet that I hope can help make sense here. If you want to find tension at the top of a circle, this right here is basically your centripetal force. You have to subtract gravity because gravity is helping pull this thing down into the middle, so the tension should be a little bit less than it normally is. The most tension you have is actually at the bottom. The reason why is tension is trying to pull up, but you have to deal with both centripetal force and gravity is actually pulling the other way. So let me solve this one then. At the top of the example, I got to find my centripetal force and gravity. Sorry, I'm kind of running out of room here. Centripetal force will be mv squared over r, and gravity will be mg. The mass actually does matter in this example then. Do I use 50 though? Good, I gotta convert this guy to kilograms. 0.050 kilograms. Because you gotta divide by 1,000, so it's 0.050. So here's how this will look. 0.050 times by, what was our velocity? Oh, we don't actually have velocity, do we?
No, where'd that mv squared over r come from?
Oh, that's what FC is normally equal to. Because this will be mass times acceleration.
Oh,
But I just realized that this formula doesn't make sense because we don't know the velocity. So I gotta use that other formula. What's that other half of the formula equal to? It was like 4 pi squared r over t squared. Is that what the other acceleration formula is equal to? But then we still need mass in front of it, so that it's mass times acceleration. Okay, one more time then. 0.050 will be the mass. 4 pi squared is just a number. The radius is 0.20. And then the period was, thank you, 1.57 seconds squared. I think I'm going to need to just erase this stuff. My work's getting too messy. At the top of the string, we have to subtract mass times gravity. So 0.050 times 981. Sorry, that's getting harder to see. Okay, let's try this. 0.050 times 4 times pi squared times by 0.2 divide by, was that number, it was exactly 1.57. And then minus 0.050 times 981. Negative 0.33.
So I can get that, and I use, there's a formula on our formula sheet that BC equals 2 pi r over t to the 4 pi.
Okay. But that's fine velocity though. That doesn't help us because we need to make our tension force equal to centripetal minus gravity. Anybody else get this negative 0.33 number?
Yeah.
Why negative?
Because it's like.
Because pulling it down into the circle. Yeah. So maybe we could ignore the negative and just say that that was going like into the circle. That's the tension. Okay, what happens when we add them? Because the other example, so this is when it's at the top. At the bottom, really the only difference then is that the force of tension is equal to, I'll rewrite it again, but 4 pi squared times 0.20 over 1.57 squared. And now we add gravity. So if you guys know how to use this function in your calculator, go second entry, just re-pull up that first number, and then add 0.050 times 9.81. And here the tension is considerably different. Now it's 0.65 newtons. Again though, it's going in, only this time in is actually going
Marty Duncan, please dial 103. Marty Duncan.
Does that make sense? If the rope was going to break, it would actually break at the lowest point. Because there's going to be more tension in the rope at the lowest point. I mean, as it's coming down on its trajectory, gravity is also pulling it downwards. When it's at the top of its loop, gravity is actually loosening the tension just so slightly on that rope by pulling the rope slightly down so the tension isn't quite as bad. But as it loops back around the bottom, the tension on that rope is actually most at the bottom. Sean.
At the top of the loop, would the gravity still affect it as much as it would if there was acceleration?
Not sure what you mean.
Like, would,
Because there was acceleration.
oh, there was,
Well, sure, because we didn't actually solve for it, but there was a centripetal acceleration. Right? That centripetal acceleration was this little bit right here is what acceleration was. So I don't know how to answer that question because there was a centripetal acceleration. Gravity was still doing its job though. So I guess what I'd like you guys to take most out of this example here, if you're solving for tension at the bottom of a circle, add gravity. If you're solving for tension at the top of a circle, subtract gravity.
But we also always have to do that little mass, like that, you just put the mass on there out of nowhere, and we don't have that as a formula.
Yeah, that's where, like, what I wrote here, did this make sense where I said FC minus FG?
Yeah.
Okay, well, FC, I kind of skipped this step, is really equal to F net, which is really equal to MA,
Oh.
and then its mass times whichever of the two acceleration formulas you want. So you could either do V squared over R, which I mistakenly did first, but if you don't know velocity stuff, then go to the 4 pi squared formula instead. Does that make sense? Okay. I've got 2 last examples. This one's probably one of the most, I don't know, cool examples to try. Roller coaster questions. I don't know. The physics behind how to make a proper roller coaster is interesting, I think. So here's the scenario here. You're going to go through a roller coaster, but you have to go a certain speed. Hopefully you guys can envision this here. If you try to go through the loop-de-loop, but you go fairly slow, a couple of things could happen. One thing that could happen as you enter your loop-de-loop is that the roller coaster would get about this high right here, and then it would just like roll backwards again because it wasn't going fast enough. The worst thing that could happen is the roller coaster goes most of the way up, gets to about here, and then like falls down and crashes. So like, does this make sense that you have to have like a certain amount of speed for this to work? Nicole.
Would the 50 be the radius of the diameter?
No, because I said the radius of 50 here. Did I do the diagram wrong?
Yeah, it says diameter.
Sorry. Let's go with 50 as the radius here. Thank you. Change this to 100 for diameter. What was that?
Anytime you go on a loop, you usually get sucked in. You feel like you're getting pushed back into your seat.
Right.
Yeah.
Yeah, but that would be your centripetal acceleration probably, right? Causing you to feel... Okay. Anyways. Okay, we want to try to find the minimum velocity. At the very top of the loop, what forces are in play at this particular point? Yep, gravity. Gravity, right? Gravity would be pulling you downwards. So what we could say then is the force of gravity is really equal to your centripetal force. We need our centripetal force to be enough to overcome gravity to make it so that you're going fast enough that you don't fall. So mg, there's gravity. Fc. Well, there's a couple ways we could write Fc. One of the ways we could write it would be mv squared over r. The other one we could do is write m and then 4 pi squared r over t squared. But I don't think that one helps us in this example here because we're looking for velocity, right?
Doesn't the mass cancel?
Good. Mass was actually irrelevant. So how do I get velocity by itself? Gravity times radius, and then square root it, and there's our velocity. This is the speed that we're going to need in order to make it through the loop-de-loop. If we have at least this speed, we're good to go. So 981 times by 50 for our radius, square rooted. 22.1. In terms of sig digs, it looks like we're going to get 3. Is that a reasonable answer? 22 meters per second is probably just under 100 kilometers an hour. Yeah, I'd say if I were going in a roller coaster, I would want the roller coaster, I mean, 1 for thrills, obviously, but 2 for my safety. I would really like it if they made the roller coaster go around the loop-de-loop fast so that I had some sort of hope of making it out alive. Does that make sense? Okay, you could make some arguments, by the way, on this question that friction would be involved, but friction at the top of the loop would actually be acting that way. Does that make sense? And so we're probably just going to ignore it anyways, but in terms of like directionality here, the friction would be trying to pull this thing backwards, and our free body diagram was really about the up and down direction, not the side to side direction. So even if we wanted to calculate friction, at least at this particular point right here, it would not have factored into our equation. That makes sense? Okay, one last example, then I'm done. Last one here. Okay, we're going to use the information from the previous question. This is the minimum velocity that the car is going to have to go around the track. If you went anything slower than that, the example I was showing you, and we're going to do this one day in a lab, if you were to try to go around the loop-de-loop, you might get up to here, and then like you wouldn't have enough speed, and you'd fall down and crash. So like this would be the just bare minimum. That being said, I don't feel like amusement parks would be okay with just the bare minimum. So my suggestion was, let's up it by 50%. And we're going to work backwards now. So if our velocity was 22.1 meters per second, how do I up it by 50%? Sure, okay, so times by 1.5. What's our new velocity going to be? 33.2?
Yeah, I got 33. I got 33.2. I got
You
22.1,
don't round your answer.
33 point, well, what would it be exactly? Let me give me a few more decimal places.
I got 33.22.
Did you use 33.228?
Yeah, we used the exact value. Oh, okay.
Are we okay with that then?
Yeah.
That's our new velocity?
Yes.
Okay, so this is well over 100 kilometers an hour. So this roller coaster is moving, which it should, it's a roller coaster. Okay, well now we're going to work backwards. We're going to try to figure out the normal force that gets exerted on the cars at the top of the loop. I want to revisit our diagram here again. So here's your loop-de-loop, and you're at the top of the loop right here. What forces are in play? Well, I ignored one last time. Gravity was in play, but shouldn't the cars, even though this is upside down, shouldn't the cars be pressing in to the track at the very top? Does that make sense? And so really what should have been happening here is there should have been a normal force as well, where the cars are actually pressing into the track. If that track were to break, this would be horrible, but the cars would then take off in that direction there. So this is a little different than the last example. Is there tension keeping you going in a circle? No. The normal force of the track is almost like the tension here. If your track cannot handle a certain amount of normal force, the track would then break. As you go around the track, the train would then like bust the track and you'd go flying off in a trajectory. That'd be horrible.
Upside down.
So, in terms of my free body diagram then, the two forces I have in play are gravity is pulling me down, normal force is pulling me up. It probably makes more sense to go normal force minus gravity, just because I think normal force is going to be bigger. So let's go normal force minus gravity. That would normally be mass times acceleration, or like say net force. But I'm going to say this is equal to my centripetal force, so this will be equal to mv squared over r. How do I find my normal force then?
Mass times gravity.
I got to add FG to the other side, so I got to add mass times gravity. We have everything we need. So mass, we actually now need mass this time though. So that mass was 4,800 kilograms. 4,800 times my radius, which was 33.2208. Square it. What was that radius again? 50 meters?
Yeah.
And then we need to add mass times gravity. 4,800 times 981. I made a mistake, guys. I just realized something. The normal force is not going this direction. The normal force would actually be going this direction. Because the normal force is the force the track pushes back on the car. Let me do this as a different example. Let's say that the car was at the bottom of the track and it's not upside down. Which way would normal force normally go for us? We'd say normal force would go up in this example. But if you're upside down, it's almost like you gotta tilt your head upside down. The normal force should be going the other way. So I made a mistake here. Your normal force plus your force of gravity would be equal to ma. So we actually have to subtract gravity. I was wondering why this was different than the last example. At the top of the track, we're gonna have to subtract gravity to find normal force. Because this would be just like tension. There should be slightly less normal force at the top of the track because gravity is kind of pulling the car away from the track. Yeah, well this is your normal force. This should be a lot of normal force.
It's like billion.
Okay.
I got 58,000.
Should I do this on the calculator together?
Yeah.
Okay, 48,000 times 33.2208 squared divided by 50 minus 4,800 times 981. I got 58,859.
Yep. Did you get 58,000? I got mine rounded to 60.
Does that make sense? So this would be the normal force at the top of the loop. And I hope I'm doing a good job of explaining this. At the top of the loop, gravity is actually pulling the cars slightly downwards. And so that normal force up there, the cars are getting pulled like just slightly away. But at the bottom of the track, gravity is going to be pulling those cars into the track even more. So when we do this at the bottom, we're going to take these exact same values right here and add them. So that would be, I'll just write it out again, 4,800 times 33,2708 squared over 50. And this time we'd add 4,800 981s. So this guy is minus, this guy is add. So take that value and add 4,800 981. So this guy, I got 1.5 times 10 to the 5 newtons. Hopefully that makes sense. As the track, like as the cars are coming into the track is going to receive a lot of force as those cars are coming so fast and gravity is helping with it. There's going to be a lot of pressure on that track as it's coming downwards. But as it's going up top, there should be slightly less pressure on the track because the cars could, if they don't have enough speed, actually fall right out of the track. Does that make sense? Let's see if I can just go to a quick demo here. I have a loop-de-loop set up. I wasn't going to do this lab until later, but. So, here's my Hot Wheels track. Flip this around. Make sure you guys can see.